From particle accelerators to understand the nature of universe, to the MRI scanners for saving human lives, superconductors and superconductivity have revolutionized science. In this video, we will understand what is superconductivity, how it works, and its applications. When we connect a power source like a battery to a wire, current flow through it. The electrons moving through the wire collides with the wire's lattice. These collisions cause the energy to be released in the form of heat, which is given by Joule's heating effect, which is normally what we experience. The battery provides this lost energy in the form of potential difference and keeps the continuous flow of current in the wire. Now imagine, we connect the wire to the battery and once the current starts flowing, we remove the battery. But the current continuously flows through the wire, without loss and without power source, for years. It will be amazing, right? This is what is happening ideally in superconductors, because of superconductivity. Superconductivity is the phenomenon in which the material is a normal conductor of current, resisting the flow of electrons. But, when cooled below a certain temperature called the critical temperature, the resistance to the flow of current becomes zero and the material becomes a superconductor. These critical temperatures are much lesser than our room temperature, and will be less than -200 degrees Celsius. The superconductivity was initially observed in Mercury but was later found to be exhibited by many other elements, like niobium and titanium alloys. The critical temperatures of different superconducting materials will be different, some may be high, and some may be low. Based on the critical temperatures, the superconducting materials are classified into high-temperature superconductors and low-temperature superconductors. The materials which exhibit superconductivity when cooled to temperatures greater than 30 Kelvin are the high-temperature superconductors. While, the materials which have critical temperatures less than 30 Kelvin are the low-temperature superconductors. For cooling high-temperature superconductors, liquid nitrogen can be used, which has a temperature around -243 degrees Celsius. For low-temperature superconductors, liquid helium is needed, which is extremely cold and costly. Liquid helium will be so cold that its temperatures will be just above the absolute zero temperature. The cause of superconductivity cannot be explained by classical physics, as it is quantum physics phenomenon. Superconductivity is caused due to the atomic vibrations called phonons between the electrons. These phonons hold the electrons together in pairs and allow them to move through the conductor without resistance below the critical temperature. One of the important and interesting characteristics exhibited by superconductors is the Meissner Effect. When an external magnetic field is applied to the superconductor, and when the temperature is reduced below the critical temperature, the magnetic field lines will be ejected from the interior of the superconductor. This effect is the reason for the magnetic levitation caused by superconductors. Remember, superconductivity also has limits. When an external magnetic field greater than a critical value is applied, superconductivity will break. Similarly, when the DC current through the superconductor is increased beyond a critical value, then also superconductivity breaks. These critical values will be different for different superconductors. This astonishing superconductivity and superconductors are used in particle accelerators, for producing very strong magnetic fields using superconducting electromagnets for accelerating the particles. They are used in magnetic resonance imaging machines MRI scanners, for producing powerful magnetic fields using superconducting electromagnets, which uses liquid helium for cooling. They are also used for magnetic levitation applications.